Okay, so we were talking about the Schrodinger equation and this letter that I should have looked up during the break, but I didn't. This represents the probability density, the probability of finding an electron at a point in space. So that would be the probability divided by the volume of the space. That s orbital is spherical, which is kind of nice because spherical starts with s. And we know that the probability density decreases as distance increases from the nucleus. So we can make a plot of this, which would be like a multiple exposure picture, where you take the same film or whatever and you expose it multiple times. So that would look like this. So each of those little dots would represent where the electron was at that particular moment in time. And so this would be like, thousands of exposures. It's important to understand that the electron is not just zinging around like a moth around a flame. That's not what it's doing. In a sense, the electron's location is spread out over the entire volume. But when we take a picture of it, we force it to act like a particle, so it has to have a location. But really what the electron really is more like is like a standing wave. We'll get to that. So if we just use probability density, this doesn't work very well because this says the highest density is at the nucleus, and we know that actually the electron is definitely not at the nucleus. So they use something called a radial distribution function instead. This works better, and I really don't see the point in talking about all of this. If you want to read about that in the book and have questions about it, I'd be happy to discuss it with you. But let's just keep to the things we really need to learn. So using that way of mathematically determining where this electron might be, we end up with a graph like this. That's called total radial probability. And it is 0 at the nucleus, and then it goes up and back down as you move away from the nucleus. And so there's the maximum probability at 52.9 picometers from the nucleus. And what's really cool is that is the same radius that Bohr predicted for the first orbit, 52.9 meters. But there's a very important conceptual difference here. In the Bohr model, the electron is always at 52.9 picometers, because it's rotating around like a planet around the sun, which is much easier to understand. But in quantum mechanics, the electron is found at lots of different places. It's just that 52.9 picometers is the most probable. So the 3s and the 2s and 3s orbitals are also spherical. All the s orbitals are spherical. And as you go from 1s to 2s to 3s, they get bigger and bigger and bigger. But we also get a node in them. So the orbital is a wave function, right? And there's points at which the wave function goes through 0. So this is a string. And if you have a string at 2 places and you vibrate it up and down, you can get a standing wave set up. And so the node is right here. And so at the node, the distance, it's hard to describe. Well, this is where there would be no probability of finding an electron. And the probability would increase as we go over here. So basically, I think the best way to think about electrons is like a standing wave around the nucleus. And we can see standing waves like this on strings, but this is two-dimensional. And the standing wave that the electron is in is three-dimensional and a lot more complicated. So the 2s orbital is going to have one node in it. So there's going to be one place where there's zero probability of the electron being there. But because the electron is a wave, it can move from one side of that node to the other. I mean, it's present in both sides, right? It's really hard because the wave can be all over, and yet when we take a picture of it, we force it to act like a particle, and then we see it at one point. Not that we can actually take a picture. And then the 3s orbital is going to have a second node. So the 2s orbital, so there's going to be this place in the middle, and then there's a region that's a node, and then there's more. And then here, we've got probability and a node, and probability and a node, and more probability. And so you could think of this shape here, no, not that one, this pink one down here, you could think of this as being like the standing wave on a string, except it's in 3 dimensions. I don't know if that's helpful or not. Every principal energy level has an s orbital. It has one, because that's L equals 0. They all have L equals 0. That's going to be the lowest energy orbital in that level. When you get above level 1 to level 2, now 2, we can have an L value of 0 or 1. So now we can have the s orbital and p orbitals. And with p, you get m sub L possibilities of 3, so there's 3 p orbitals, unlike the s where there's just 1. So these 3 p orbitals are oriented on different axes relative to each other. So this one, they have a node, so this one has a node at the nucleus. So this is aligned along the x-axis, this is along the y-axis, and this is along the z-axis. And of course, you know, the atom is moving in space, but this is just them relative to each other. And this is where I think the idea of the standing wave is easier to visualize. Now that's getting kind of close, right? So this p orbital is like a standing wave along this x-axis. And this is like a different standing wave over here. And this is a standing wave going this way. Can waves of electromagnetic radiation pass through each other? Can different light sources go through each other? Yeah, they can. So there's a flashlight from my phone, right? And we've got light coming up there, and we've got light reflecting out there, and we don't see them like colliding or forming a storm or anything. They're just passing through each other, right? So is it a problem if these orbitals overlap a little with each other? No. Because they're waves, and waves can overlap and pass through each other. When you get to n equals 2, now we've got 5d orbitals, and those are even stranger. They look like this. These guys, I can see. You know, it's like, oh, well, it's kind of a double p, and these are aligned kind of wonky to the p orbitals, and then there's this weird guy that's like a p orbital with a floaty or something. I don't know. And then F, stranger still. Now it looks like we're getting into balloon art, right? Weird, 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 weird. You should know the shape of an s orbital. It's a sphere. And the p orbital is kind of the dumbbell, like 2 balloons, right? D and F, nah, they're weird. So these orbitals are essentially waves, right? Waves can have positive or negative values. Like when we looked at the interference between waves, right? We could have two waves that are in phase with each other, or we can have waves that are out of phase with each other. Well, the waves that are electrons also have a phase, positive or negative value. And when those orbitals, those waves interact, their wave functions can be in phase or out of phase. And so they can reinforce each other or they can cancel each other out. And we'll get to that later. The p orbital is the easiest for me to get on board with. So the p orbital is like a standing wave that has one node, and this side is positive, that side's negative and this side's positive, or whatever. This must be negative because it's down, and that's positive. But these are opposite phases. An s orbital is just going to be positive or negative. So we've got all these weird shapes for the orbitals. Then why do we think of atoms as being spheres? Because if we take all of these orbitals and superimpose them, this is representing all of those wonky balloon shapes, right? Together, they form a sphere, right? Maybe not perfect, right? It goes in and out a little bit, but you get the idea. It's composed of all these standing waves, and overall, it's a sphere. The atom. Not strange at all.